Okay, so conservative forces. These are forces on which the work does not depend on the path that's taken to get there. Okay? It does not depend on the path, right? We can zigzag all over no matter what, but it doesn't matter in terms of the amount of work done. Okay? These are things like gravity, springs, right? We don't care when we're overcoming gravity if we take the staircase to get there or the elevator to get there. It doesn't matter. All that matters is the displacement that we had compared to those vertical forces. Okay, same thing works with the spring. We don't really care if it bounces back and forth and back and forth and back and forth. We only care about its starting place and its ending place. Okay, so it's not a path force. Okay, so those are conservative forces. Non-conservative forces are other types of forces for which it does depend on the path. Things like friction, tension, any type of applied force. Those depend on the path that it takes to get there. Okay, so those we would consider non-conservative, which means they are not conserved. So we can only define the potential energy for forces that are conservative, right? We haven't talked about the potential energy in friction because it doesn't exist, right? We only are talking about the potential energy of conservative forces, which are things like gravity and springs, okay? Potential energy itself looks at the starting point and the ending point, which means that's why we look at conservative forces. Most importantly, gravity and springs. Okay, we've looked at potential energy of those. We have both sets of equations for that, yes? Potential energy of a spring and gravitational potential energy. Do we have both of those? Yes. Okay, good. Those are both of the potential energy equations that we'll use throughout the rest of the chapter. We won't have any extra for just potential energy. Okay, so now we can take this work energy principle, which is the change in kinetic energy is equal to the net work. We can add potential energy into that equation. Okay, this is for non-conservative forces. We can take the total energy of the system and equate it for work. Okay, we can't look at only potential energy, but we can look at the combination of the two for non-conservative forces. Okay, because we already talked about things like friction, tension, applied forces. They don't even have potential energy. So in order for them to be incorporated into the work energy principle, we have to include kinetic energy as well. Okay, so the total work of a system is equal to the change in kinetic plus the change in potential. So, we've talked about the work done by non-conservative forces. Now we're going to look at the main portion, the main chunk for today. Okay, the principle of conservation of mechanical energy. If conservative forces are acting, right, things like gravity or the springs or things like that, okay, if those types of forces are acting, total mechanical energy of a system neither increases or decreases. Okay, you can abbreviate that if you want, but the mechanical energy is the total energy of the system. So from here on out in this chapter, we're really only going to be focusing on those conservative forces, things like gravity and springs. Okay, those are the two that we can deal with, and we can look at the total energy of the system. When we talk about friction or tension or applied forces or things like that, it gets a little bit more complex than what we need to do. So we're going to focus on just those conservative forces that give us a simple mechanical energy or total energy of the system. Okay? All right, so mechanical energy is sum of the kinetic and potential of the system at any moment. So this capital E gives us the total mechanical energy, okay? And it's really just energy in itself. This equation is not 100% necessary yet either. what you really need is this bottom equation, okay? We can combine the energies into one form of conservation. Okay, so here is the equation for a pinpoint or a spot in time, right? If we want to find the energy at one point in time, we would use this equation, kinetic plus potential. If we want to look at the conservation of energy in 2 points in time, this is what we would use, right? Kinetic plus potential equals kinetic plus potential. And that bottom equation with the box around it is what we're really looking for here. Okay? Rarely would we ask to find the energy at one point. Usually we're going to look at the change in energy between 1 point and second point or whatever, things like that. Okay? Usually we're going to be comparing 2 different points in time. But if we needed just one, you would be able to use this equation here. Okay, what do we imagine that mechanical energy is going to be measured in? Joules. Good. Right. Same as kinetic, same as potential. Okay, so we talked about at any point, right, at one single pinpoint along the path, we can find the energy at one point, and all we're doing here is expanding these equations out, right? This 1/2 mv squared is equal to kinetic energy, and mgy is what type of potential energy? Gravitational, not the spring, right? What variable do we need to have in it for it to be a spring equation? We have to have k. Good. Okay, so this is at one point in time. So what do you think our next set of equations might look like? That's right. That's right. We're going to be able to combine this. So if this is one pinpoint of time and we want to find the energy, we're now going to be able to combine them. We'll be able to combine them into the conservation of energy equation, but expanded. Okay, so all we're going to do is take it basically and set this equal to final energy. Okay, y is the height and v is the velocity. We know that, I think, pretty well, right? Okay, from our equation so far. So here is our total mechanical energy conservation equation. Okay, energy at one point equals the energy at a second point, which means kinetic plus potential equals kinetic plus potential. And all we're doing here is we're combining these and really expanding them out into their complete equation form. Okay, so all we're doing is little substitutions to get down to this final big equation. This is the big one. Okay, this right here is the big one that needs to be on your equation sheet for sure. Okay, all 4 terms. If you're not going to have any of the other ones, that's fine. You can get there using this equation. Okay, so all the other equations that we kind of worked with up until this point were to get us to this big one. I like to always keep my equation in order of kinetic plus potential equals kinetic plus potential. Sometimes we'll use all 4 terms in our equation. Sometimes we might not have any kinetic energy at the final point, right? So that might just be a 0. Sometimes we might not have any potential energy at the first point. That might be a 0, right? So I'm going to account for all 4 terms in my equation, but sometimes they might be zeros and make our equation a lot simpler. Okay, does that make sense? Okay. So we looked at the kinetic and potential, and we're going to start looking at the connection between those two, right? If I hold something in the air, what type of energy does it have? If it's not moving, but I'm holding it above the ground? Potential. It has all potential. As it starts to fall to the ground, what happens? We start transforming into kinetic. If it's halfway to the ground, does it have both types? Yes, it does. Okay, so we have to understand it's still off the ground. It still has potential to fall and potential to do work. As it gets to the ground, or the instant before that object hits the ground, we've transferred to all potential. Okay, so it's a sliding scale as we go downward as something falls through the air. A sliding scale from all potential to more kinetic, more kinetic, more kinetic, all kinetic. Does that make sense? Okay, so think about that sliding scale. All right, if the height of a stone is 3 meters, calculate the stone's speed when it has fallen to 1 meter above the ground. Okay? You can use, right, you would be able to solve this using kinematics equations, but that's not how we're going to solve them. Okay, we're going to solve them using conservation of energy. All right, so let's start picking out some variables here. Okay, so it's fallen from 3 meters to a height of 1 meter. So let's start looking at our equation. If I have kinetic plus potential equals kinetic plus potential. Okay, at its highest point at 3 meters, what type of energy does it have? All potential. So this is all potential. Okay, as it reaches 1 meter, what does it have? It has both, right? Potential and kinetic. Okay, if it had reached the ground all the way to the bottom, it would have all kinetic, but that's not the case, right? It didn't fall all the way to the ground. It fell to 1 meter above the ground. Okay, so that means when we look at our equation, we'll use this term, and this term, right? We always like initial on this side and final on this side. Okay, I like to have my initial on the left and final on the right. So as we start plugging these in, when I plug these into my equation, I'm going to say that kinetic energy is 0, and I like to account for that. Okay, so I like to go ahead and plug that 0 in. You don't have to do that. I like to make sure I know I've accounted for all of my possible options. Okay, so 0 plus m times g times y equals 1/2 m times v squared. We're solving for v plus m times 9.8 times 1. Okay, you'll notice that mass is not given, right? So I just left an m. We're going to work through the algebra, and I'll show you how that cancels. It won't end up making a difference. It won't have much effect on it. But I'll show you how we get there. Okay? We don't have to plug in negative 9.8 here for gravity, because we're doing work to overcome gravity. So this is 29.4 m equals 1/2 mv squared plus 9.8 m. Okay, what would be my next move algebraically from there? Get the m's on the same side, right? So that means I would subtract my 9.8 m to the other side. Okay, from there, I can either cancel my m's right off the bat, that's fine. Okay, right, I've got an m on either side with no other addition or subtraction. Do I want to multiply by 1/2 or divide by 1/2? Divide by 1/2, which is really multiplying by 2. Right, so I'm going to get 1/2 to the other side, which leaves me with 39.2 equals v squared. So I square root that, and I get a velocity of 6.3 meters per second. Okay, and this stone is falling in which direction? Down. Falling down, so you have to include that negative, right? We took the square root, so the math's not going to do it for you. So you have to go make sure that you include that when it's falling in the downward direction. Okay. Questions here? All right. I told you this chapter loves to use roller coasters for an example, so you'll see lots of questions about roller coasters. Okay? So go ahead and get written down what you need. You'll probably be able to do this one on your own. All potential. Then at the bottom, what do we have? All kinetic. Okay, I know we don't necessarily know, is the roller coaster still off the ground or is it at ground level? Okay, we have to kind of zoom that out and we have to understand that's as far as that track is going to let it fall, which means that is at its ground level. Okay, does that make sense? So even if the roller coaster is maybe, 5 feet still off the ground, we don't know that for sure. If we do know that, that would make a difference, but right now we're going to assume that's at its ground level, right? It doesn't have the potential to fall any farther while it's on that track. Okay? So that means we have all potential, all kinetic. So we would say 0 plus mgy equals 1/2 mv squared plus 0. Okay, so I plug those zeros in so I make sure I understand has all kinetic and all potential or vice versa. Okay, so 9.8 times 40. 392 m equals 1/2 mv squared. We can cancel our m's, divide by 0.5 and square root, and we get a velocity of 28 meters per second. Okay, this one's not in free fall, it's still moving forward on its track. I'd be okay if you made it negative because it's going in the downward direction, but since it's moving forward on a track, I'd keep that one positive, right? It's not in a free fall type situation. I'd probably take either one there. Okay? Other questions? All right, good. Keep this one in mind. Okay, so at what height will the car have half of this speed? So if its maximum speed is 28 meters per second at the bottom of the hill, at what height would it have half of that speed? How many of you automatically think 20 meters? It'd be too simple, right? Yeah, that's too easy. All right, so we have to actually calculate it, half that speed, okay? Here's my roller coaster. It's going to reach half that speed somewhere in the middle here, right? Okay, so if it starts with all potential, it's going to reach it somewhere in the middle, right? We don't know if it's halfway. We don't know if it's more toward the top or more toward the bottom. But what do we know about the energy at this point in the track? What types of energy would it have? Both. Okay, so we've got to know that we're looking at both types of energy there. Okay, so we know that this side is 0 plus 9.840 m equals kinetic plus potential. And we are solving for y. What do we know our velocity is in this case? We know that it's 14, right? Half of that original max speed. Okay, so here I'm going to combine my like terms. And then I can cancel my mass. You don't have to wait that long necessarily to cancel mass, but okay, so did we end up with a y equals 30 meters? So that's 30 meters from the ground. That's not 30 meters below, right? 30 meters from the ground. So about right here, it's already reached half of its speed. Okay, so it picks up a lot of speed at the beginning, and then it will finish out to the end. Okay, questions here? So this is a spring equation. So if you want to write this equation on your equation sheet, you can. It's still going to be kinetic plus potential equals kinetic plus potential. Okay? But instead of mgy, we're going to use 1/2 kx squared equals 1/2 mv squared plus 1/2 kx squared. Thank you. You're welcome. Okay, so that's the only thing that changes. If you want to write that equation on your equation sheet, that's a good one, right? Because that's going to be for springs. Or if you just know, okay, to use 1/2 kx squared for potential energy, that's great also. Okay, this is 1/2 mv squared here. Okay, so it's the same thing, 4 terms, but instead of mgy for our potential energy, we're going to use 1/2 kx squared. Okay, so mass is 0.1. Spring is compressed 6 centimeters. What are we going to have to do to that? Convert it to meters. Good. The dart detaches from the spring when it reaches a normal length, right? When it gets back to 0, what speed does the dart acquire? So, when we look at this spring to begin with, it is compressed 6 centimeters. When it gets to its final point right at the end, it's back to its static position. So our x value is not 6, but 0.06 meters. Okay, here's our origin. Here's our 0 point right here, because that's its static position. It's been compressed, which is technically a negative 0.06. When we square that negative, it's not going to make a difference, right? It's still going to come out positive. But when it gets to this point, which is its final, does it have potential energy anymore? No. And does it have any kinetic energy at the start right here when it is compressed?
No.
No. So this is all potential and this is all kinetic. Okay, so when we set up our equation, we'd say 0 plus 1/2 kx squared equals 1/2 mv squared plus 0. Okay, are we clear with why that is the case? As it's compressed, that dart's not moving, right? It's being held at 6 centimeters compressed. As the spring releases, that dart's going to release when we are no longer have any potential energy. Okay, they told us was 250. This is negative 0.06.